So the talk is Theoretical Computer Science for the Working Category Theorist. It's the title of a book that I wrote and was accepted for Cambridge University Press. So it's coming out. It's going to be the first in a series of books on applied category theory. I just want to say about this talk, it's the first time I'm giving this talk. So if you see errors or you have some comments or suggestions about making a better presentation, feel free to send me an email or drop me a line. That would really be helpful. I think I plan on giving this talk to other places, and so I want to get it in perfect shape. Okay, so this talk is a preview of a forthcoming book. I said this already. The book uses basic category theory to describe all the central concepts and proves the main theorems of theoretical computer science. I assume you, okay, anyways. So we're going to meet, let's just skip down. We will meet some of the deepest ideas and theorems of modern computers and mathematics, Turing machines, unsolvable problems, the P equals NP problem, Gödel's incompleteness theorem, the Halting problem, etc. I will report on new things I learned about theoretical computer science and category theory while working on this project. I promise you, you will not learn anything new about category theory. Okay, so I'm not teaching anything new about category theory. What I want to do, what my aim here is to show you is that the right way to learn theoretical computer science is using category theory, and the category theory that we're going to use is not very sophisticated. It's not that sophisticated, but it's I think well, it's nice. Now the book is about 150 pages. I actually wrote about 210 pages, whatever. They wanted the book down to 150 pages, so I chopped out the rest and I put some supplementary chapters on my webpage. But the point that I'm trying to make is that there's no way you're going to see everything. I'm just going to highlight some things that I learned about category theory or about the relationship between theoretical computer science and category theory in this talk. So it's like a hop, jump, skip around the book to see what we can learn. Okay, so we're going to go through an overview, and then we're going to talk about different models of computation, a little computability theory, a little complexity theory, a diagonal theorem, and then I'll tell you what's in the supplementary chapters, and then this part about what I learned. In other words, what I learned that I didn't know beforehand, or what I found surprising. Okay, so here's this picture of all the categories that most of the categories that we're gonna see in this talk and in the book. I'm gonna spend about 15 minutes trying to get this picture into your head and show you why it's an important picture. It took me about a year to get it straight, and so you can spend 15 minutes seeing it. Now that I have it, it's quite obvious, and it can't be anything else, but it took a long time to get it straight. And this is the picture that's in that highlights that I gave out, and you might want to just print that out and have it on the side just to mark it up, because you'll see it makes sense. So we're going to spend the next 15 minutes understanding what this picture is. Let me just give you some orientation. All the categories that you see in front of you are essentially symmetric monoidal categories. They're not, and I'll show you where it fails. Okay, they're essentially symmetric monoidal categories, and I'll explain to you that's the way to think about it. Okay, all the horizontal lines are inclusion functors, okay, which are bijective on objects, essentially. So that's nice. Okay, now all the functors, most of the functors you see are pointing to that central line. So we're going to explain what that central line is and tell you what it is. Okay, so you have func, computable func, and total computable func. I'll tell you right now, this is all functions whatsoever. This is computable functions, and that means functions that computers can compute, and this is total computable functions that are totally computable and are computable, and they are total. Every input has an output. Okay, so I'm sorry. Hold on. Okay, that's the central line. Then the next slide, the thing outside that central line are also computable functions, but with a restricted set of domains and codomains. And we're going to go through each one of those individually. And then outside here in the red and the blue and the green, those are models of computation. And the question is, what is a model of computation? What is a computation? So Turing says a computation is something that manipulates strings. Okay, Post said that too. Others talk about register machines. What's a computation? It's something that manipulates natural numbers. Okay, so that's what this is all about. And of course, real computers, they talk about circuits, and circuits are things that manipulate strings of booleans. So that's what this is all about. Okay, and so we're gonna go through this slowly. I just want to point out the main thing is all these functors are going down, and what they are is as follows. Every Turing machine accepts a bunch of strings and sometimes outputs a bunch of strings. Okay, so you have a Turing machine that accepts a bunch of strings and outputs a bunch of strings. Well, that defines a function. Okay, that defines a function of, from strings to strings. It defines a computable function. So basically, the Turing machine goes to the function that it describes. The register machine goes to the function of natural numbers that it defines. The circuit goes to the function that it defines. Okay? Okay, so let's focus in on this center line. Okay, you have functions, computable functions, and total computable functions. And let's just go through them. Functions, the objects are all types. By types, I mean reals, integers, natural numbers, strings, powers of natural numbers, a real cross a natural number, cross a whatever, all types of, every single types. I don't get very sophisticated. We have powers, we have strings of types, but I don't get into anything extremely sophisticated. Okay, the morphisms between them are all functions. Okay, and composition in the category is simple composition of functions, but down here it is a symmetric monoidal category structure. Namely, you can multiply the two functions in parallel. The fact that it's symmetric just means that if you f times g is somehow related to g times f. Okay, so that's that. Now, a subcategory of that with the same types, in other words, all with the same objects, all types, is computable functions. What can a computer compute? And that's going to be the main thing. And a sub, and again, this is also inherits. It inherits the same symmetric monoidal category structure as here, and a sub symmetric monoidal category of that is total computable functions. And again, the objects are all types, total computable functions, and symmetric monoidal function. It's a symmetric monoidal category. Okay, great. So now let's build out from there. So now that we have the center line, let's build out from there. A subcategory of computable functions is computable functions, but the types are only powers of strings. In other words, string, cross string, cross string, et cetera, et cetera. Okay, those are powers of strings. So it fits in there nicely. Here you have a subcategory of computable functions. The types, it's a full subcategory. The types are powers of natural numbers. Natural numbers squared, natural numbers cubed, natural numbers ... et cetera, et cetera. Okay, and here you have Boolean functions, and those are going to be like strings of Booleans, strings of Booleans squared, pairs of them, strings of Booleans cubed, triples of them, et cetera, and we go on. Okay, and these all are subcategories which deal with total morphisms. Let's just go through the things. Strings, the objects are powers of strings. There are computable functions between powers of strings, symmetric monoidal category, same thing for that. Same thing for natural numbers. Okay, this is going to be dealing with register machines. We're going to have computable functions, symmetric monoidal functions, total computable functions, et cetera, et cetera. Okay, and again, powers, bool is a little bit more complicated. You can't just have powers of bool because that's finite. Okay, there's only a finite amount of the stuff there, and that you don't want. So you want strings of Boolean strings, and then you're going to have powers of strings of Boolean. So strings of Boolean powers like that. And again, everything is nice and orderly and symmetric monoidal category. Okay, Noah said before, if you have any questions, write to him and he'll unmute you, and then you can ask away. I have no problem. Okay, great. Now let's talk about these functions, okay? Computable strings, these are powers of strings, they clearly include into computable functions. This is all types, this is strings of types, okay? So this includes into this. Now, there's a morphism going the other way. In other words, if I give you any piece of data in any type of...
Noson, can I just stop you for a second? So what I've realized is that Zoom is sort of lying to me, and it turns out that anyone can unmute themselves. And if I give someone the privilege to unmute themselves, it automatically unmutes them and makes a weird noise. So you actually now have the privilege to unmute yourself and ask a question. You can do that, but please don't, grief the chat. So thank you.
Okay, perfect. Okay, so the interesting is the morphism going the other way. So again, if you have any sequence of, if you have data in any sequence of types whatsoever, you can encode it as a string, okay, as a power of strings. Okay, so that's this morphism going this way. Now, you don't get an equivalence of categories here. This is not an equivalence of categories. You get something which I've never seen before. It's slightly weaker than equivalence of categories. And I essentially, well, whatever, instead of saying this is essentially surjective, I say it's inherently surjective. And I can explain what that is another time. But there is a relationship, and again, it comes from, this is clearly an inclusion, this is clearly not an inclusion, but an encoding, and once you can encode any type of data into strings of data. Same thing here. You can encode powers of natural numbers include into all types, okay? However, you can go the other way. Take any type of data whatsoever, you can encode it as powers of natural numbers, okay? This is what computer scientists do. They take data of one type and encode it into data of another type. Same thing here, but here you can see a little bit more clearly why I needed strings of Boolean rather than just Boolean, because I wouldn't be able to encode all data as just a power of strings, of a power of Booleans. I need strings of Booleans. In other words, natural numbers can store any natural numbers. Strings can be of any size. Booleans can also be of any size. Okay, that takes care of it. So that explains what these strange morphisms. But the important thing is they go both ways, but they are not an equivalence of categories. And that took a long time. I thought they were, and got to some bad days. Okay, great. Now let's build up. Out here are these models of computation, and we're going to go through each one of them individually. I just want to say every single computer science, theoretical computer science textbooks usually chooses one model of computation and works through that also. We also will just choose Turing machines in a few minutes, but we have to take cognizance of the fact that there are other models of computation, and we have to see how they interact. For those of you who know the literature, Sipser uses Turing machines. Davis and Wayuka, they use register machines. Corman, Lizason, and Revesz, when they talk about NP completeness, they talk about circuits. A lot of people talk about circuits. Barak and Moore, they're in their complexity book, they talk about circuits. So everybody talks about different things, but again, they are all in some sense equivalent, and we have to talk about that, and they all describe elements over here. Okay, good. So let's talk about Turing machines. Okay, I'm assuming you know what a Turing machine is. It's just you have input tapes. Usually a Turing machine is done with one tape, and we'll talk about that in a second. But here you can have M input tapes, you can have N output tapes, and you can have K work tapes. And the point is, you're in some state at every point, and these I's are going left and right, moving all around, and changing the data as you go along. Okay, and there's a question of, do you allow the data to be changed on input tapes? Do you allow only writing, or can you read also from output tapes? But we don't go into that. But this is what a typical Turing machine looks like. Okay, great. Now we have to talk about the category of Turing, and I believe this is the first time it's defined. The objects are natural numbers. Okay, so that's the object of the thing. And the morphisms are Turing machines. So a morphism from the natural number m to the natural number n is a Turing machine with m inputs, m input tapes, and n output tapes. M like Mary input tapes and n output tapes. And I don't care how many work tapes you have. Okay, that's not the important question. That's not the important thing. Okay, so you have that. Now, does this form a category? Answer: no, it does not form a category. Okay, and there's two major problems with it. One problem is when you compose Turing machines. Let's just talk about how you compose Turing machines. You're going to have a Turing machine with this inputs to that inputs, okay, to that outputs, and then you're going to have another Turing machine where basically you're going to make the outputs of one tape to be the inputs of another Turing machine. So you're going to have the inputs and outputs, okay, and that's easy to define. The only thing is it's not associative. Okay, because that transfer of data is not associative. But it's even easier, so it's not associative, but it's even easier to see the problem. A more easier problem is there's an identity Turing machine. There's a stupid Turing machine that takes all the data from the input and puts it on the output tape. Okay, it just moves along, and it's a simple Turing machine to write. Anybody can write that Turing machine. Okay. And you can compose that with any other Turing machine. So you have this stupid identity Turing machine composed with another Turing machine. You compose it, you will get a Turing machine. It will do the same function as the original Turing machine, but it's not the same thing. It is not the same thing. This thing and this thing, which does nothing else than transfer the input to the output, compose, is not the same thing. Okay, so we have to be aware of that it's not the same thing. Okay. This category, or it's not a category, it forms a bicategory. Okay, so we're going to have two cells, and the two cells are basically going to be isomorphic two cells that basically are generated from saying when two Turing machines are essentially the same. They're essentially the same because of this associativity. Okay, this associativity and this problem with the units. We have a problem with the units, and it is not a category. Okay, let's talk about its monoidal structure. Okay, basically, if you have a Turing machine, the monoidal structure is placing two Turing machines side by side in a sense. If you have a Turing machine with m inputs and n outputs, and you have another Turing machine with m prime inputs and n prime outputs, then you can put them together and you get a Turing machine with m plus m prime input string tapes and n plus n prime output tapes. Okay, and I don't care how many work tapes you have, but if you have k work tapes in one and k work tapes in another, you're going to have k plus k prime work tapes in both. So it does form an isometric monoidal bicategory. Okay, same thing with the total Turing machines. Let's go on to register machines. Register machines are a little less well known, so I just thought I should tell you what a register machine is. Register machines are methods for manipulating natural numbers. Turing machines manipulate strings. These manipulate natural numbers. These machines are basically programs in a very simple programming language where variables can only hold natural numbers. The programs use three different types of variables, namely x1, x2, x3, called input variables, y's called output variables, and guess what? Work variables also. We're going to see this over and over again. Registered machines employ only the following types of operations on any variable. You can increment a number, you can decrement a number, and you can you can do what's called the conditional branch. Now, there are different ways of defining register machines. Everybody has their own definitions, but the point is they're all equivalent. Not only are they all equivalent, but they're equivalent. This is the amazing thing about register machines is this simple programming language can do anything that any other programming language can do. They're equivalent to any other programming language. So that's an amazing result. A program is a list of such statements for various variables. The values, okay, the rest just says there are some register machines that are total. There are some register machines that can get you into an infinite loop. And we have to worry about that. Okay, so the register machines, again, the objects are natural numbers, okay, and the morphisms are register machines. Okay, so I have to tell you, The morphisms from M to N are all register machines with M input variables and N output variables. So it's just like Turing machines. There we were talking about strings, and here we're talking about natural numbers. Okay, this also is a symmetric monoidal bicategory, and for the same reason, it's a bicategory for the same reason. Composition is bad. Composition is perfectly fine. Associativity of composition is bad, and the units don't work. Okay, the units don't work. If you compose, you have a silly identity register machine that just takes everything from the input variables to the output variables. I can write that machine. You can compose it with another register machine. You don't get the same thing as this. You get another register machine. Now they're equivalent, they perform the same operation, but it's not the same. Good. Okay, let's talk about circuits. Okay, you know what circuits are. This is a circuit with 6 inputs and 2 outputs, and we're going to talk about that. Okay, so let's talk about the category of circuits. Again, the objects are natural numbers, and the morphism from M to N are not circuits, not what you would think, circuits with M inputs and N outputs, but rather circuit families. You have to understand that these things will accept several strings of Booleans. Circuits accept several strings of Booleans. Now you ask yourself the following question. Okay, fine, it's going to accept a string of Booleans. What's the size of the string of Booleans? Okay, and so we have to talk about not a circuit, but a family of circuits. And basically what that is a computer program that you input the number of how large your input is, and it will output a circuit. The computer program will output a circuit of that size. So that's what a circuit family is. It's a computer program that accepts a number and it outputs a circuit of a particular type. Okay, so you want to add 2 numbers. Let's say just adding 2 numbers. Okay, well, I say I want to add 2 binary numbers. So you can't do that. You can't build a circuit for that because I don't know how big your circuit is. How big is your inputs? So what it is, when you say you want to add 2 binary circuits, you're not talking about a circuit. You're talking about a whole family of circuits. Okay. Braided monoidal bicategories. This also fails to be a category for the same reason. Yes, you can compose circuits, but the composition is not associative. And moreover, the identity circuit, which just takes n input strings and outputs n input strings, it's basic straight lines, okay? You can easily compose that circuit, but that's not the same thing as the original thing, as the original circuit. So if you have a circuit and you compose this stupid straight lines, then the circuit is not the same. Okay. Now it has a monoidal structure, and that monoidal structure is basically taking one circuit and taking another circuit and putting it side by side. The disjoint union, the co-product of in the category of circuits. Okay. So this is also forms a bicategory, and it works. Okay. The one idea that I got out of this is that the more physical you get, in other words, beforehand we were talking, oh, question, why the hell is it braided? Okay, why is it braided? Everything else I said till now was symmetric. Why is it braided? And the answer is yes. If you have 2 circuits, you can swap them like this, but you're crossing wires. Okay, and if you cross wires, you can cross wires this way, or you can cross wires this way, and they're not the same. Okay, and so that's where you get the braided axiom. So that's interesting. Okay. The more physical your models are, the less structure there is in the collection of all models, okay? So when you're dealing with computable functions are very mathematical. But when you start dealing with physical things, well, Turing machines aren't physical. There's no such thing as a Turing machine because it has an infinite number of tapes. There's no such thing as a register machine because it can hold any natural number. There's no such thing as these circuits because we don't have programs that can list off these things, but it's closer to physical things. These are, the more physical your models are, the less structure there is in the collection of all such models. And that's an important thing, especially to an applied category theory seminar. I just thought I should say that. So it's harder to describe some of the things. Go ahead.
The 2 cells in this case, is the isomorphism class of morphisms joined by an invertible two-cell, all the ones that compute the same partial recursive
Yes,
function?
yes, yes. So if you have an isomorphic, right? So here's something you can do. You can take this symmetric monoidal bicategory and quotient it out, and just make any two things, any two morphisms equivalent if they have a two-cell in between them. And that's totally legitimate. But then you're not talking about, let's say, Turing machines. What you're talking about is equivalence classes of Turing machines, which is fine. But then you have to worry about a lot of other things. Okay, so I didn't do that. I talk about it, but I didn't do that. Make sense? Okay, good.
Yes, but I think it's actually finer than computes the same partial recursive function, because there may be fundamentally different ways of computing the same function.
Okay, and I talk about that later on when we talk about algorithms, as opposed to just doing
Great.
it. So I'll get to that. Okay, great. Now so I'm sorry. So we're now finished the big picture. Okay, so we now understand that, and you have a copy of it on Noah's webpage, and you should get it tattooed and live with it forever and ever. I want to simplify that picture a little bit here. You have Turing machines, register machines, circuits, and you have computable functions in between. And that, somewhat simplifies the things. But what there are other things to talk about is reinterpretations of one computing model into another computing model. And like I said, most textbooks use only just one computational model, but some of them talk about ways of reinterpretations. Let me just tell you, your handheld calculator is a calculator that's basically a register machine, although it can deal with other things besides the real numbers. But really, the operating system in your handheld calculator is telling what the circuits should do. So that's in some sense a functor from here to here, from register machines to circuits. There are also Turing machines to register machines, and or the other way around. The interesting thing about this, so these are reinterpretations of one model into another model. And again, as category theorists, we have to look at all models of computation. We can't just look at one, we have to look at all of them. It's a moral imperative. Next, I just want to point out, in every one of these, all these diagrams must commute. In other words, if I have a Turing machine and I reinterpret it, or it's really a compiler, and I get another model, I better make sure that the computational function that it performs is the same thing. So these triangles have to commute. However, there's no reason for the outer triangles to commute. Okay, I can change a Turing machine to a circuit, I can change the circuit to the register machine, but it doesn't have to be that that's the same thing as the Turing machine to the registers. And obviously there are many different ways of reinterpreting, and I don't get into that. Hold on. Here's another thing. Not only do these models describe computational functions, they also describe logical formulas. Okay, now I'm going to go through this a little bit quickly. In the book, I go through it carefully, whatever, but there's also a category of logical formulas. Okay, and the category, you can almost make out what it is. Okay, I'm going to give you the shortened version, but it's slightly wrong. You'll be able to see it in the book. The objects, it's also a symmetric monoidal. It's a symmetric monoidal category, not a symmetric monoidal. Maybe it's a bicategory. I have to look it up in a second. Whatever, I won't look it up. The objects are natural numbers, just as you would think. Okay. The morphisms are as follows. The morphisms from M to N are sequences of logical formulas with M input variables and N, and there are N elements in the sequence. Okay, so you have a logical formula, a logical formula, a logical formula, a logical formula. You're going to have N input variables and M input variables and, I'm sorry, M as in Mary input variables, and N output and N formulas. Now, the reason why you want to think of that is because if you have you should want to think of a logical formula, or I'm sorry, you want to think of a sequence of logical formulas as a function from Booleans to Booleans. Okay, so if you have a sequence of a sequence of n logical formulas in m variables, then you want to think of them as there are m inputs, and the outputs, when you evaluate those formulas, you're going to get n Boolean outputs. So that's the way to do that. Now, I've simplified it because you have the same problem as you had before. You need families of logical formulas. Okay. Now, the main point I want to get out of this is, again, the outer triangles can commute, whatever, but here I think even the inner triangles can commute. But the total Turing, there's a way of giving a logical formula for how a Turing machine acts, and so that's this function. And we use this function to get some logical results that correspond to the relationship between logic and computation. And I'll show you that later on. So that's what this formula is. Again, both of these are monoidal, I'm sorry, symmetric monoidal, maybe logic is not symmetric, but they're monoidal, at least bicategories, and these are monoidal functors. Okay, here's another thing, namely all these things can be enumerated. Okay, you can enumerate Turing machines, you can enumerate whatever, computational functions, whatever. Now, if you notice, I'm taking disjoint unions. These maps are not functorial. These are maps of sets to the discrete category of natural numbers. So they're maps of sets to numbers, okay? And I will talk a little bit later on about this. This was a failure on my part. I thought I was trying to make this functorial for a long time, and it can't be made functorial, and I will talk about that. Okay, so you now have the big picture, and we are ready to start talking about computability theory. So let's talk about computability theory. Computability theory asks the following question: what can be computed and what cannot be computed? And so that big diagram that I had, I'm only going to look at the top spoke of it. Okay, there's 3 spokes. But I could do whatever I'm doing, I could do with any of the other 2 spokes. But just for historical reasons, we're going to talk about Turing machines. Okay, and if you notice, so every Turing machine corresponds to a function between powers of strings. The m is going to go to string to the m. That's the object. The object m is going to go to string to the m. The Turing machine from m to n is going to go to the computational function, the computable function that this Turing machine describes. Same thing with total Turing machines. Okay, we can shorten that. We don't need that strings thing because really that includes into that. So this is what we're doing. And now we can clearly state what computability theory is all about. Computability theory determines if a given morphism in func over here is in computable func, is it in here, or is it in total computable func? Another way of looking at this is to consider the following functors. You have Turing goes into func, and total Turing goes into func. And we can ask, given a morphism in here, is it in the image of this, or is it in the image of this, or is it not in the image of either of them? Okay, and then it's called non-computable. Okay, so this is just, my goal here is just to show you, I'm not trying to teach you anything new in computability, in theoretical computer science. My goal here is to show you that category theory is a perfect glove for theoretical computer science. And that, it fits perfectly. Okay, so let's give you the paradigmatic example of something that's not computable, or not computable as you want it to be. The halting problem, this goes back to Turing. There is a total morphism in func, okay, that takes 2 natural numbers and outputs a Boolean, and it's defined as follows. It's 1 if Turing machine y on input x halts. It's 0 if Turing machine y on input x does not halt. So this is the halting problem. And this is what Turing's 1936 paper shows. Halt is not a morphism in total computable functions. Okay? It's not clear such a thing is a total function. It always outputs, so it's not a morphism in computable functions either. It's just a morphism. It's just a function. Okay, God knows the answer to these questions, but human machines don't. Okay, now I've been around long enough that I know that it's not smart to prove a theorem, especially a theorem that you've probably all seen. But what I want to do is I'm not going to prove a theorem in a lecture, but I want to show you how the theorem can just be stated as about morphisms in a thing. So this is a snippet of the proof. So this is a decider. This is a recursive function. You have an input here, and it decides yes or no if the input satisfies something or not. Okay, this is a recognizer. You have an input here, and it decides yes or maybe. Doesn't give an answer all the time of whether or not some object's in here. And one of the parts of the proof of the Halting problem is that you can build a decider with two recognizers, a recognizer for f and a recognizer for f complement. Okay. Okay, and it makes sense. You know, the number goes in, it goes into both. You parallel process both of them, dovetailing, whatever it is. And if the answer is yes, then this will come out. And if the answer is no, then this will come out. But the point is here, you get a yes/no answer built out of two recognizers. I just want to show you what this looks like in the book. That's what this looks like. Okay. It's a sequence of morphisms in a category. Let's go through it. You have a sequence of types. It goes into pairs of sequence of types. That's exactly this. Okay, and then you do f composed f. You do f twice, but here you compose it with a not. So you're going to get the complement. Okay, and then here is a function that takes two booleans and outputs a boolean. The two booleans are a and b, and if a is 1, then the output is, let's say, 1, and if b is 1, the output is 0. Okay, so that's a simple Boolean function that takes 2, and it just depends which one of these are 1. Now ask me, what happens if both of them are 1? Well, that won't happen here, so we don't have to worry about that. Okay, great. Now, the Halting problem is just one problem in that, but there are many others. So this is called the non-empty. Here's a nice function. It takes the natural numbers and outputs a Boolean. Okay, if Turing machine Y has non-empty domain, in other words, if it halts at some input, okay, then output a 1, otherwise 0. Now we show that Halting problem reduces to non-empty domain problem as follows. Here's the Halting morphism. There's a morphism like that, such that this commutes, okay? And now here's a statement about category theory. If this is in total computable function, and H, we know H is in total computable function, so if this is in total computable function, then the Halting problem is a total computable function. But we know that the Halting problem is not a total computable function. Conclusion, this is not a total computable function. So it just goes very smoothly. Okay, it's about composition of morphisms and which category they're in. Very smooth. Okay, okay. This is just in general. You have reducing one decision problem into another decision problem, and that's what this is all about. Okay, and the way to think of this is as a comma category. This is like a slice category, but a comma category. This pulls out, this is the single object category, it pulls out functions, pulls out the Boolean thing, and we're including the morphisms here. All these morphisms have to be total computable functions. Okay. Okay, so here are other undecidable function problems. The non-empty domain problem I showed you. The empty domain problem, that's another one. The equivalent program problem, let me just tell you what that is. Given two programs, tell if they produce the same function. That is a non-computable thing. That is a non-computable, it's non-computable, computer can't do that. The printing 42 problem. Given a program, tell me, is there any possible input which I can get an output of 42? Computers can't tell that. And again, it falls simply out of this makeup, this setup. Rice's theorem, any non-trivial semantic property of Turing machines or any computational model is undecidable. Okay, Gödel's incompleteness theorem. Now, usually you think of Gödel's incompleteness theorem as a logical result, and I guess Gödel did think of it as that. However, even Gödel, or it's either Gödel or Bernays, already saw that it can be looked at as a consequence of Halting's of the Halting problem. You can look at Gödel's incompleteness theorem as a consequence of the Halting problem. So that's a nice thing, and it follows exactly from this thing. A little bit that LT, which goes from Turing machines to logic, you need a generalization for that. Okay, you have to generalize that functor a little bit. Okay, and Turing's original paper was about the Einstein's problem, which is about given a logical formula, tell if it's valid, and you cannot. There's no mechanism to do that, and again, it falls out of consequences of the whole. Okay, so that's the end of computability theory. Let me talk about complexity theory. Complexity theory doesn't deal with what's computable, it deals with what's computable efficiently. Okay, and so what we have to talk about is we have to measure total computable functions. Okay, and so here's a nice measure. Let me just talk about this. We're going to have this is the set of functions from the natural numbers to the real number star. It's a rig, it's a single object category. It has a lot of structure, but we don't use all the structure on purpose, and I'll explain to you, the last slide, I'll explain to you why. But let me just tell you what this is all about. For every total computable function, you want some other set function from the natural numbers to the non-zero real numbers, and basically that tells you, well, this function can be done, depends, what's the size of the input, that's how many operations it will take, or that's how much time steps it will take to do that. Okay, again, given a computable function, you're going to get another computable function that's going to tell you, for input of size n, f of n operations will have to be done. Now, this is a measurement for deterministic Turing machines. I did not describe what non-deterministic Turing machines are, and I won't. And this is measuring how much time it uses. However, we can have other types of measures also. We could talk about deterministic machines and how much space it uses. Now, by space, I mean those work tapes. How many spaces in the work tape does it use? You can't talk about the input tapes because the input tapes is how many inputs it has, and the output tapes, you don't want to measure that too, but how much calculation. And the intuition is, this is an intuition in complexity theory, the more complicated a function is, the more space it demands, okay? But you can also measure things in non-deterministic time and non-deterministic space. So you get these morphisms like that. Now, what's the purpose of these morphisms? Answer, you can get complexity classes. Let me show you what a complexity class is. Complexity classes are not problems, they're categories, nice categories, and we'll talk about it. So take a subset S of these functions, and I'll show you some nice ones in a second. Take a subset S of these functions, take the measure from that, and then take a pullback of this. Okay, the pullback of this, okay? And then you're going to get this category. Deterministic time, those problems that can be solved in deterministic times with, okay, these are not decision problems. Those problems, these are those programs that can work in deterministic time with this, within S time. So S is telling you that function, okay? So the objects of this is what we're defining here. The objects are all types, just like the objects here. The morphisms are vastly smaller than that. The morphisms are vastly smaller. There are only those morphisms. There are only those computable functions which can be done in S time, okay? We could do the same thing for D space, N time, and space. Now, question, how are these different things related to each other? How are these different complexity classes related to each other? And it goes as follows. There are three different dimensions of relations. Okay, we could talk about space and time. Okay, and this is somewhat of a natural transformation. The idea is as follows. If you need 30 boxes to calculate something, then one thing for sure, you're going to need 30 time steps to calculate things. Okay, because every box that you're using in your Turing machine it's going to demand a time step to move from one box to the next box to the next box. So the amount of space that you use is less than the amount of time that you use. Another thing, another relationship between these things is determinism is a special type of non-determinism. So if you can solve a problem in deterministic time, then you could definitely solve a problem in non-deterministic. Non-determinism means you can do many things at one time. Well, determinism means you can do one thing at one time. So this is a special type of this. Okay? Okay, next thing is subsets versus sets. Second, I have to open the tuna fish.
Peanut butter.
Peanut butter, okay. Subsets versus sets. So we have three different things. Let me show you what I mean by that. We can see all three of these dimensions of relatability in one diagram. Given T, a subset of S, and both of them are subsets of this, we have the following, okay? Now let's just follow this. The left side is all about determinism, and determinism includes into the right side, which is all about non-determinism. All these are perfectly legitimate functors. Okay, we have to talk about the monoidal structure here. There's not really, okay. Let's talk about the front. The front is all about time. Oops. And time includes into space. No, space includes into time. Oh, no, time includes into space. Okay, no, that's right. Okay, time includes into space. Okay, and let's do one other thing. The bottom is T. T is a subset of S. So T is smaller than S, so we have that. Okay, and there are other relationships between these things, but we'll talk about these relationships for a second. Now, let's talk about some more interesting subsets of this rig. Okay, that's a rig. Okay, there are constant functions, there are logarithms functions, there are polynomial functions, there are exponential functions. All of them are subsets, and what you get is this whole hierarchy of complexity classes. And again, there are more relationships, and actually we can prove that some of these inclusions of categories are proper inclusions of categories. So that's nice. Okay, we're going to see in 2 minutes, that's always a hard thing. How do you show that it's proper? Steve, you have a question, go. Okay, when Noah's going to let you in.
Yeah,
Oh,
can you hear me?
perfectly, go.
So does the fact that something like P is low for itself, does that have a sort of useful interpretation in terms of a diagram like this?
By low in terms of itself, you mean if you had an oracle?
Yeah.
Okay. So I do talk about it, and I'm not in this talk, but yes, I have a whole section on oracle computation and the way, and I think it can be stated in that way. Okay.
Cool. Thanks for answering.
We're going to see this in a second, at the end when we talk about Baker, Gill, and Solovay, and Savage is there. Okay, great. So we're moving a little bit quickly here. You can also talk about decision problems in complexity theory, and we have the same type of idea about reductions, okay? But here, we don't only want these H's to be total computable functions, but we also want them to be computable in polynomial time, okay? And so you get, again, this common category, like this, and this pulls out bool, and this includes into this, and you get this common category of all decision problems. Great. Let me show you some famous subcategories of this decision problem. You can take all non-deterministic time polynomial algorithms. Again, this picks out bool, so we're going to talk about decision problems. We're going to include determinism into that. That's an inclusion. We could also talk about the deterministic time polynomials, and again, Boolean, this is an object in here is a Boolean. This is the identity, actually. And we're going to take the common categories, but these things include into each other, okay? These complexity classes include, well, these complexity classes include into total computable functions, and so you get an inclusion of comma categories, and P is a subset of NP, which is a subset of decision problems. So this is a proper way of saying the P is equal to NP problem. We know that this category is a subcategory of this. We don't know if it's a full, well, by the way, the objects of these categories aren't bijective, so we're just talking about whether or not it's a full subcategory or not. Okay, I'm not going to answer the P equals NP problem in this talk, simply because there's not enough time. No, but I do have something to say about the P equals NP problem. I don't think it can be solved categorically or anything like that, but I do think that category theorists can contribute in a profound way to this question. Okay, great, but maybe we'll talk about that afterwards. Okay, question, what's a complete problem? Okay. A morphism from one decision problem F to another decision problem G means that G is as hard or harder than F. The hardest problems in the complexity class is a problem that every problem maps to it. Such problems are called complete in that literature, but we category theorists have another way of talking about it. The collection of all complete problems in a complexity class is the subcategory of weak terminal objects. Let's just go through the definition. A terminal object is an object that every object has one morphism. Exactly one morphism. A terminal object is a weak terminal object can have more than one morphism. So you can have a lot of morphisms to it. So all complete problems form weak terminal objects. Let me just tell you one interesting thing about weak terminal objects. If you have a weak terminal object, okay, and you have a morphism to another object, then the other object becomes a weak terminal object also. Okay, and so that's a very simple thing. And the hard part, of course, is to find the first weak terminal object. And that's called the Cook-Levin theorem. Okay, great. Okay, some of you who have seen some of my work before, I have this paper on diagonalization, okay, and I revisit it here where I just focus on theoretical computer science. And I'm not going to go through it here, but this simple theorem, okay, this simple theorem, it's Lever's theorem from 1963 or something. This simple theorem describes self-referential paradoxes in a simple, clear way. And what I do is I focus just on computability in theory and complexity theory, and I get results for it. Hold on. Okay. There's also the contrapositive of the theorem, and again, I'm not going to state it. It doesn't pay to state it, whatever, but it's almost every instance of self-reference and diagonalization proof falls into this simple format. This is, like I said, category theory is perfectly, is a perfect fit for theoretical computer science. Let me just show you some of the results I get. Okay, these are results from computability theory. First of all is Cantor's original result. Well, that's not computability theory, but there does not exist an onto function from the set of natural numbers to the power set of natural numbers. So there's different levels of infinity. The unsolvability of the halting problem, we saw that already, but you can see it as an example of diagonalization. There is a computable function that's not primitive recursive. In the book, I talk about primitive recursive and generating. It's a category, the category that primitive recursive functions generate, but it's not all computable functions. And there is a total unary function that is not computable. That's something else. And the recursion theorem, which is a very deep theorem in computability theory that has lots and lots of application. All these can be done with Lever's diagonalization theorem. Okay. Okay, now complexity theory. Okay, so some results of this diagonalization using the complexity theorem. So there's a space hierarchy theorem, says that there are computable functions which can be computed in space of H. H is some function describing the input-output relationship, but not less than that. Okay, so there's a way of, so you give me more space, you can program more problems, you can solve more problems. The time hierarchy theorem is a little bit more complicated slightly. There are computable functions which can be computed in time of H, but not in much less time. Okay, the word much is on purpose. Okay, we were talking about oracle computation before. I'm not sure everybody knows what it is, but there's a Baker-Gil-Sullivan theorem which says there exist oracles A and B such that P to the A is equal to NP to the A and P to the B is not equal to NP to the B. This not equal is done by a diagonalization. The Ladner's theorem, which is, I mention it in the book, but I don't prove it in the book, but it's worthy of just saying it over. I think everyone should. This is a very important theorem. It says if P is not equal to NP, then there are an infinite number of complexity classes between P and NP. Okay, so that's an interesting result. Another result is I just found out recently that the Immerman result about log space and colog space, that they're equal, is also a diagonalization. And I think it can be put into this thing, although I haven't worked it out, the details. But it's not in the book. Okay, great. Oh, sorry. Okay, so we did computability theory, we did complexity theory, we did this diagonalization proof. And again, the editors of the book wanted only 150 pages. They didn't want to go beyond that. So what I did was I chopped out some other things and I just put it on my webpage. They're available right now. You're welcome to steal it, whatever you want. I just go through a little bit of formal language theory and show this hierarchy of different languages and different computers. I talk a little bit about Kolmogorov complexity theory. I'd like to spend 3 minutes talking about cryptography and algorithms, simply because, again, to show you that category theory is the right way to talk about these things. So I want to talk about cryptography. Alice wants to communicate with Bob. The encoders and the decoders must be total and computable. You want them to be computable functions. You want them to be total computable functions, and morphisms in total computable functions. We shall work with some subcategory of total computable functions with the same objects, namely all types, called easy. Okay, so it's not a very good name, easy. Now, I'm being specifically hazy. That's an oxymoron. I am being hazy about what easy is, because I'm being vague about it, because there are a lot of different options of what you want, especially when you start talking about quantum computation and things like that. So easy is easy things to do. I give 4 or 5 possibilities of what I mean by easy. Any morphism not in easy will be in hard. Okay. Now, the morphisms not in a subcategory don't form a subcategory. Okay, so they're just they're a set of morphisms. So you have easy as a subcategory, and then you have a set of morphisms in total computable functions, but they're hard. Okay, encoders.
Can you say that the composition of 2 hard morphisms is hard?
Oh, can you say that? Yeah, I guess you would want to say that, yes. But it doesn't have identities.
Right.
So there's a fancy name for that, nuclears or nucleos or something like that. Anyways, but yes, so it does not form a category. So encoders are in easy. You want to be able to easily compute your things. Now, I was always thinking that decoders should be in hard, but they're not. Okay, it took me a long time to realize that. The intended receiver of the secret message should be able to easily decode the message. In other words, the decoders, D, which goes from a sequence of types to a sequence of types backwards, are also in easy. Okay, when you send your secret information to Amazon, they have to decode you with ease. Okay, great. It should be hard. It should not be hard to decode. Rather, it should be hard to find the right decoder. Okay, so it took me a long time to understand that. The notion of a trapdoor function will be helpful. It is hard to find the right decoder. However, with the right key, it will be easy to find the right decoder. So let's formalize this in terms of categories. A cryptographic protocol that encodes data of type A into data of type B consists of a set of encoders, which are a subset of easy, a set of decoders, which are a subset of easy, notice going the other way, and here's an inverter function. This is the most important thing, which takes, the inverter takes an encoder and outputs a decoder. But the inverter is in hard. Okay, so again, these morphisms are easy, but the inverter is hard. and you want it as follows. You want this to be a good, legitimate inverter. In other words, if D is equal to invertible of E, that satisfies that if you encode something and you decode it, you get back to the original thing. You can also put in the other, E composed D should equal to the identity of sequences of B. You can put that other requirement in also, and it's used a lot in cryptography for doing things. Okay, great. Well, we need something else also. A key function takes for every encoder, you want a sequence. This is also in hard. Okay, you don't want the key to be easy. You want everyone to have the encoder, but you don't want them to be able to calculate the key, such that for all E, there is a key, K of E, which is the key of it. Okay, and then there's a trapdoor of function, and I'll show you what this satisfies. This is the important thing. The trapdoor takes the keys and gives you the decoders. Okay, and this is the commutative diagram that you want. You want every encoder, there's a decoder, okay, and that's your inverse key, your inverse thing, and then you have a key and you have a thing. This is in hard, this is in easy, this is in hard. Okay, which makes sense. So hard can equal composition of this. And basically what it says is the trapdoor function with the key is equal to the inverter of that function. Okay. Now, the amazing thing is almost every major by the way, this is a definition. There's absolutely no theorems there at all. I didn't make any theorems whatsoever. But the definition, every major cryptographic protocol falls into this simple format. Okay, so it's the beginning. You can now start talking about these things. And of course, the main question is what's hard, what's easy, and stuff like that. Okay. I want to finish up a little bit early. I want to finish up because I want to get to the lessons. So Steve Huntsman mentioned this last talk, and I wanted to just bring it up. I was talking about these. These are those computational models. They're called the programs. So you can call them Turing machine, register machines, and whatever. And these are functions. Okay. And so for every computable function, there's the set of computational models that there's the set of computational models that compute that function. So here we have sort, and here we have, let's say, find max. Okay. Okay. Great. Now, this one has 4 lit up. You have merge sort written by Alice, and you have merge sort written by Bob, and you have quick sort written by X, and you have quick sort written by Y. Okay, now merge sort and quick sort are 2 different algorithms. Okay, so you might think of an algorithm as an equivalence class of programs. They all give you the same function, but they're an equivalence class of programs. And the question is, what is, when are two programs equivalent? Why is this program equivalent to this program? Okay, and you might say, well, they use different variables, but they're the same. Or they do 2 disjoint processes in a different order, so that would make them the same. Okay, and it's a subjective question, when are 2 algorithms the same? But the point is, you can look at all of this as you have programs, and then you have a quotient algorithm. You have a quotient function to algorithms, and you have a quotient function to computable functions. And again, the objects are all sorts, but all possible types, and you have that. Now, again, this is somewhat telling when 2 algorithms are the same is a somewhat subjective question, and for every possible answer to that subjective question, you have a certain amount of structure that you can have. Now, you can move this all the way down, this algorithms all the way down, and say 2 programs are the same if they produce the same function. Okay, that's not what we use the word algorithm for, but that's fine. You can use that. Okay, and then the category of algorithms will have a very strict structure, just like the category of functions has a very strict structure. In contrast, you can move this up, okay, and say two programs are similar. Two programs are similar if they are the exact same program, and then you can move this up. Okay. Now, for those of you who know about lambda calculus, we're talking about beta equivalences and U equivalences and stuff like that. Anyways, so this is a nice way of talking about algorithms. They're equivalence classes of programs which are a sub-equivalence classes of functions in some sense. Okay, this is the domain of computers this is the domain of software engineering. This is the domain of mathematics, and this is the domain of computer science in a sense. Okay, great. So now, in 5 minutes, I'd like to tell you some of the lessons I learned from this thing. Rather than considering the set of isolated decision problems, we work with the category of decision problems. So it's decision problems with their reductions. That's the most important things. They are comma categories. In complexity theory, these comma categories form complexity classes. Complete problems, they are weak terminal objects. I said that already. Interesting thing, there are a few major results. Halting is undecidable, SAT is NP complete, the recursion theorem, and many corollaries are derived from these results, okay? They just fall out of it from this way of us setting up the problems as decision problems and comma categories. So it falls out of composition. It falls out of composition, okay? Surprisingly, adjoint functors did not play a major role in the tale, we told, okay? And I was thinking about why. In computer science, there are many equivalent ways of making constructions. This is not conducive to universal properties. So I didn't find a lot of adjoint functors. I did find Kahn extensions, and obviously Kahn extensions are adjoint functors, but there are ways of forming complicated minimizations and maximizations which are used. So you can describe them with Kahn extensions. Okay, let's go back to that logic functor. We defined a functor LT from the symmetric monoidal bicategory of total Turing machines to the symmetric monoidal bicategory of families of sequences of logical formulas. This functor was used to describe the workings of a Turing machine with logical formulas. The functor L of T and extensions of the functor were used in the proofs of the following theorems that relate computation and logic: Gödel's incompleteness theorem, the unsolvability of the unshyness problem, and the Cook-Levin theorem, which says that satisfiability is an NP-complete problem. So it's just amazing that it all falls out of this one functor. Okay, and the one functor is relating Turing machines, computational devices, and logic, so you expect that. Okay, this diagram showed up over and over and over again, and I've never seen it before. Maybe some of you did, okay? And so it's a diagram like this. You have this two triangles, and the two triangles assume to commute. This is an inclusion into this. I call this a density function, okay? In other words, in some sense, A is dense in B, okay? Now, it's not really dense, so this is a weakening of reflective equivalence. It's not really dense. It's not an equivalence of categories, because the inclusion composed F is not equal to the identity. So if you go here and go there, it's not. But you take an object here and you do F of it, it's going to give you the same C object that you had. Okay, so in that sense, let me just show you where it shows up. Okay, every Turing machine is equivalent to a Turing machine in Turing 1.1. So every Turing machine that you saw probably has one tape. Okay, sometimes it has two tapes. Well, this one, they're equivalent to a 1.1. Okay, so let's just go through there. This is Turing 1.1, Turing machines with only one tape. This is Turing machines with as many tapes as you want. And obviously there's an inclusion in here, but there's a way of encoding many tapes into one tape. Doesn't give you the same Turing machine, but it gives you the same function. So we see that over and over. Okay, every logic circuit has an equivalent NAND logic circuit. So the computer that you're reading this document, that you're watching this thing, has only NAND circuits, not ANDs and ORs. Okay, and the reason for that is NANDs are somehow nicer. So again, this is NAND circuits, this is all circuits, and they produce the same function.
So Is C in the same category as A and B?
No,
Okay,
no,
so those lower arrows
are
are
functors.
image under a functor?
Yes.
Okay.
Okay, and the way to think of it is these are the functions that these computational models produce. Okay. Okay. Every non-deterministic Turing machine has an equivalent deterministic Turing machine. Okay, so this is deterministic. It includes into non-deterministic. You can go that way, but it doesn't give you the same thing. Sorry. Savage's theorem, which is a theorem about complexity theory of space. Every NP, non-deterministic polynomial space computation, has an equivalent p-space computation. Okay, so let me just give you Savage's theorem answers the P equals NP problem is about time. Question, what about space? And Savage answers this, I think in 1973, he said NP space is equal to P space. Okay. This is something about the Baker-Gill-Sullivan thing, which is not worth going through, but things of a certain type are of things of another type. Every non-deterministic finite automaton has an equivalent deterministic finite automaton. This is in that supplementary chapter. Okay. Now, just as a footnote, an interesting footnote, this relationship between non-determinism and determinism is not universal. It doesn't always happen that every non-deterministic has an equivalent. And here's two examples. Not every non-deterministic pushdown automaton is equivalent to a deterministic pushdown automaton. And if P is not equal to NP, and I think it probably is, then not every non-deterministic polynomial algorithm has an equivalent deterministic polynomial algorithm. Okay, by the way, if they are equivalent, then it would just be another example of these things, relationship between non-deterministic and deterministic. Okay. Okay, where did I fail? Or where, well, I failed, but I'd like to think other people's will fail too. While our aim was to be as categorical as possible, we found that twice we had to go outside the bounds of categories, not outside, but just talk about sets rather than categories. One, it was those enumerations. Okay, enumerations of models of computation or of computable functions are not functorial. If you have a number for a program and you have a number n for this program and a number for this program and you compose them, then the composition, that number of the composition will probably have nothing to do with n and m. Okay. Another thing, complexity measures. Okay. Complexity measures also doesn't respect composition or the tensor product. Let's just talk about it. Let's say I have a very a program that takes a very long time to do that, and a program that has a very short time. Okay, then I compose it. This one goes first. This one goes second. It doesn't necessarily, the measure of the complexity doesn't necessarily have anything to do with each other. So that was an interesting, and again, I tried, but they really, and they're not made to. So it was hard to define those measures, and no, not hard to define. I can define them perfectly. It's just they're not categorical. I mean, the definitions are not very categorical. Okay, thank you. Any questions? And thank you for listening. And again, this is the first time I'm giving this talk. So if you have any criticisms or mistakes or something like that, either tell me now or send it to me a private email.
So how does Cartesian closeness come up in this?
It does come up. I just avoided it simply because I didn't want to get into it. You saw it some places. For example, in that cryptography thing, you saw it there, right? Because we have the inverter goes from a Ham set to a Ham set, so it's there. But I avoided talking about it simply because I didn't want to get into that.
Okay. I have a question.
I have a question about the bi-category structure on, I think it was Turing, the category Turing.
Right.
So, I mean, maybe the question just begins with, can you explain what the two morphisms are?
Okay. So the two morphisms. So I told you it's not associative, and it doesn't satisfy the unit, right? Okay. It's not associative and it doesn't satisfy the unit. So what I did was I put a two morphism in between two of those, which F compose G compose H, and F compose G compose H, different, they're associated in different ways. I put an isomorphic two morphism in between them. And then you have to generate, and also there's an homomorphism between the identity composed F and F. Okay, so again, those are not the same thing, but I do two morphisms. And then what I say is the two morphisms are generated by those types of things.
Interesting. So are there non-isomorphic two morphisms?
No.
Okay.
No. Right. No, all the two morphisms are isomorphisms.
Interesting. So the picture that I have in my head is sort of relating to cobordisms, where like the identity, I don't know if you know anything about cobordisms.
Yes, yeah.
The identity cobordism, when you sort of append it onto the cobordism, it's not like equal. You have to homotopy, you know, is that sort of similar?
It's very similar, and especially when you talk about circuits, because think about what the identity circuit is. Well, it's a wire. It's n wires. Okay. Well, how big is the wire? Well, it's very small. It doesn't have to be big at all. Well, how big is it? Very, 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 very small. Okay. But say again.
You could take it to a length.
Right. Anyways, so like my calculus teacher said, dt over dx is a very, very small arrow. Anyways, again, as long as it's something, then it's not the same thing. Now you could, like you said, you could take the homotopy class of it and you can mod out, and that's perfectly legitimate. Okay, and I do that in my algorithms paper also. The problem with that is you're no longer talking about Turing machines or register machines. You're talking about equivalence classes of Turing machines and register machines. And then you get trouble. Now you have to ask yourself the question, are they the same in terms of complexity theory? And the answer is probably yes, but you have to worry about all these different issues.
Mm-hmm.
Yeah, thanks.
Hi.
Hi, hello.
I had a question. Lavier's paper on the diagonal argument requires Cartesian closedness, but I didn't see a mention of that here. As there's a reason it's not necessary here.
It's not necessary at all. And not only that, in Lavier's book on conceptual math and in his mathematics for sets, he brings it in. All you need is a product. You need a product and a diagonal map. That's it. You don't. In his original paper, he does have it, but it's not necessary.
I see.
And in my paper explaining Lavier's paper, I don't talk about Cartesian closedness. It just makes things more complicated and less readable. Cartesian closedness.
I see. Thanks.
Any more questions?
One presentation thing. When you
Please.
talk about powers of naturals, there's a tiny bit of confusion whether you're talking about tuples or multiplication. That, you're talking about a tuple of integers, not about 4 to the 3rd power, which is 64.
Okay, I'm sorry. Right. N tuples of integers.
Yes.
Right. So those are the possible inputs and outputs. N tuples and M of inputs. Sorry. Thank you.
So I have another question that might not make any of this easier to understand, but it's sort of something that popped into my mind. When you were drawing the arrow of P into NP into decidable, and you were talking about how there's some extra categorical structure there. And I guess you said something about how, the functor was essentially surjective, but the question is about fullness. So my question, long story short, is do you think that there are even higher structures on P and NP than just categorical? Like 2 categorical, 3 categorical, or infinity categorical?
Let's just go through what the objects are. The objects are decision problems. So those are morphisms from any types to bool. Okay, and the morphisms are reductions. there's a problem already here with the tensor product, okay? Because the tensor product, it doesn't even go smoothly with that. I don't see why there should be higher morphisms. I mean, the morphisms are programs that output a Boolean, so the decision problems. I don't see what your higher cells would be, but I do think that computer science category theorists have something to contribute to the P is equal to NP problem. And if you indulge me for 1 minute, I'll actually say what it is. And the idea is as follows. There's an intuition. It's an intuition. It's not a theorem in any sense. It's hard to make that theorem, and maybe category theorists can make the theorem. That the difference between P and NP is that the search space in P is very well structured. You have a lot of structure for the search space in P. In other words, you can use a lot of operations to find the answer. As opposed to that, the search space in NP is usually not very structured. It's usually, I don't know, the traveling salesman problem. So you have, you know, the subset sum problem. So you have a giant tree, a binary tree of, you know, what's in your elements and what's not in your elements. So binary trees are not very well structured, whatever the hell that means, so that the only way to actually search through them is to do what's called a brute force search. So again, NP, the only possible way of doing it, since it doesn't have a lot of structure, the only possible way of going through it is to do a brute force search throughout that. As opposed to that P, let's take the Euclid's algorithm, which is about natural numbers. Well, because you can multiply natural numbers, because you can subtract because you can divide natural numbers, it has a lot of structures. So therefore, you can solve P very, very quickly. You can solve those things in P. Well, category theorists are experts in describing how complicated structures are. It would be nice to somehow make that intuition somehow formal. In other words, category theories use algebraic theories, operads, monads, triples, two operads, whatever, all this extra structure. They have all this machinery in which we can describe structures. So I'd like to know the following question. What is an easy structure that is in P, as opposed to that, what's a non-easy structure that's an NP that, you know, and again, what we're looking for is that dividing point, which I don't think you're going to find in category theory, but what's the dividing point that says, oh, this is an easy structure, this is a hard structure, and the hard structure can't have more structure to it. So it's just, that's a categorical way of looking at the P as NP, the P equals NP question.
I think you very much answered my question. The question was more so, is there some extra categorical structure that might be missing? And I think that was answered there, or at least the fact that the intuition is there is what I was thinking.
Right. Yeah. Although I've never seen the intuition written anywhere, but the intuition is true. I think the intuition can be formalized using category theory. The search spaces are different. The search spaces have more structure, and the search spaces don't have more structure. Any more questions? Anyways, it's a pleasure. Thank you.
Yeah, well, there's a question in the chat, actually. They're asking about when your book is coming out, if you want to plug that.
Next year. Here it is. On my webpage. On my webpage is the first 30 pages. And if you, well, I'm not allowed to say this in public, but if you send me a nice email, maybe I'll send you something else. But anyways, on my webpage is the first 30 pages, and the supplementary chapters are on my webpage. And I'm going to put this lecture on that webpage, link to it.
Great. Well, thank you again so much. That was a great talk.
Okay, thank you. Thank you for listening. I'm going to